Good morning. I am Arnab from Indian Institute of Technology, Kharagpur. So today I am going to give a talk on how ZnO thin film can be used to sense hydrogen selectively. So before I begin my talk, I must mention that the majority of the work has been done by the first author. Since she could not be here because of health issues, so I am giving the talk on her behalf. So why do you need to detect hydrogen gas? Hydrogen is a highly combustible and odorless gas, and because of low molecular weight, it has a tendency to leak, and it is highly combustible, and it has a very high cross sensitivity to carbon monoxide. So in this work, what has been done, three methods have been used. Firstly, using activation energy, secondly, using the response versus temperature, and thirdly, using the principal component analysis, we have selectively identified hydrogen from carbon monoxide. Now, one of the major solutions for detecting hydrogen is the semiconducting metal oxides. Here you are using zinc oxide. Now, zinc oxide is easy to fabricate. It has low cost, small size. It can detect low concentration of gas, and because it is a semiconductor and it's an N-type semiconductor, which means the majority carriers are electrons. So we can utilize that fact and changing of resistance due to exposure to gas, and we can detect any test gas like hydrogen or carbon monoxide. This is the market share for different kind of mechanism used to sense hydrogen gas. Now, how did we fabricate the ZnO thin film? Initially, we took a precursor, which was zinc acetate dihydride, then a solvent, methoxyethanol. We mixed it, we heated it at 80 degrees centigrade. After that, we added few drops of stabilizer, which was monoethanol amine. After that, we coated it on the quartz surface. Then we intermediately heated at 300 degrees. Then we heated at 600 degrees for annealing. And this is the final substrate, where we have a gold coating on the surface for measuring the conductivity. Now, this is the measurement setup. Initially, we have the two gas chambers. One is air, another is the test gas, which is hydrogen. We have a flow controller and a temperature controller. So these two are controlled using the monitor, and then we have a electrometer, which gives a steady voltage, and we measure the change in current, and thereby we measure the change in resistance or conductivity. So these are some of the characteristics of ZnO fabricated. As you can see, this is an X-ray diffraction pattern which shows pure phase, hence there are no impurities present. The scanning electron micrograph shows that the grain size is of the order of mesopores from 2 to 50 nanometers, which is ideal for Langmuir adsorption. These are the gas sensing characteristics. Initially, the air was introduced, and we let the resistance stabilize to a baseline. After that, the test gas was introduced, and because hydrogen is reducing gas, so the resistivity dropped, and then again we stopped the gas flow, and the resistivity again rose back to its initial value. As you can see, for 300 degrees centigrade, the recovery was more accurate, rather than in other temperature range, the recovery was not so specific. There's a parameter defined S, which is defined by your initial resistance minus the resistance you got after introduction of the gas divided by the final resistance. So this is a very strong function of the concentration of the gas as well as on the temperature. Next, we use the resistivity data to fit a conductance curve, and which was given by, we have initial value and we have some exponential terms. So now this was done for both for hydrogen and carbon monoxide, and using the Langmuir adsorption kinetics, we found these curves and fitted these values, and we got the values of G0, G in the G, and these are the values. As you can see, the values are quite different for hydrogen and carbon monoxide. The optimum temperatures here, as I said previously, is 300 degrees centigrade, and the values are taken for that temperature only. Now, we can calculate the activation energy from the response time. If you take the natural logarithm of the response time versus the inverse of the temperature, the slope of the linear curve gives us the activation energy. So using this, we can say that the activation energy obtained for hydrogen and carbon monoxide are quite different, and this can be used to detect hydrogen from carbon monoxide. Next, we used a equation which is given in this reference. So this is we fitted the there is sensitivity use and the temperature, and the A0 is the pre-exponential constant, and all these values are we obtain from the fitting curve, and what we get is the value n, which we get from this fitting, and this n value is different for hydrogen and carbon monoxide. If you want to, the equation is given in detail in this reference. Now, if we vary the concentration of the gas from 5 ppm to 500 ppm, and we want to look at the value of n again, so we have to take the natural logarithm of the sensor response and the concentration, and the slope of that curve gives us n. So as you can see, that n value obtained across different concentration of the gas is same as you obtained theoretically in the previous slide. Now next we did the principal component analysis to separate between hydrogen and carbon monoxide. So during the principal component analysis, what we did was we took the conductance transient and took the Fourier transform of it, fast Fourier transform. So what we got, the amplitude and phase information, and using that amplitude and phase information we got two basis function, and we created two principal components, and using these two principal components for two different temperatures, we see that for hydrogen it lies in a certain region, the clustering is in a certain region, and for carbon monoxide the clustering is in a different region. And this is another method. So finally, you can conclude by using the three different methods, using activation energy, using the sensor response versus temperature curve, and the principal component analysis, we could selectively detect hydrogen from carbon monoxide. So if you have any questions, you can direct the questions to the author.